Before starting the next lesson, try this warm-up. What is the measure of angle x in each case? So here's the first case, here's the second case. Pause the video, try to answer the question, and then check back in to see how you did. In the first one, we notice that we have opposite angles. Opposite angles are always equal, so x is 60 degrees in the first case. Here, there's a couple ways you can look at this. First, just look at the big triangle. Two sides are the same, which means this is an isosceles triangle, which means these two angles must be equal, so they're both 40 degrees. Another way you can look at it is look at the two small triangles. Well, the two sides are the same, they have the same angle, and then this side is a common side, so they have side angle side similarity. Similar triangles have corresponding angles equal to each other, so again, they're both 40 degrees down in this corner. Okay, so either way you look at it, x is 40 degrees in the second case. Now that was just a little bit of a recap of some ideas that we're going to use when we talk about circles. So this lesson is about the properties of circles, or circle properties. So our goals here are for you to be able to determine the angle between two chords. So we'll review what chords are and how to find the angle between them. You should be able to determine the measure of the arc subtended by two chords, or the arc length. We'll talk about what that is. Determine whether two lines are tangent. So we'll talk about what a tangent is. And then also determine the perimeter of a polygon which has a circle inscribed within it. More on that in a few minutes. Before we get into the properties of circles, let's start with some terminology. So I've drawn two circles here and some lines on all the circles. And these lines represent parts of circles that I'm going to define. So we're going to get some words here to describe different parts of a circle. Okay, I'll start with what we're most familiar with. This blue line here from one side to the other going through the center, that's called the diameter. Half of that distance, so from the center to the outside of the circle, that's called the radius. So hopefully you already know those terms. If you have a line that just touches the outside of the circle at one point, that's called a tangent, or a tangent line. Now, if you have 2 points on the circle connected to each other, regardless of where the 2 points are, as long as both points are on the circle and they're connected to each other, that line segment is called a chord. Okay, now here's a radius. Here's another radius. The angle in between the two radii, that's called the subtended angle. This distance from here to here along the curvature of the circle, this is called the arc length. And this area in here, this is called the sector. So all these words can be used when we're talking about circle properties. Feel free to jot these down so that you can refer back to them, especially for the unfamiliar terms. Before we do any examples, we're going to talk about some angle theorems. These are the inscribed angle theorems. So we're talking about angles within the circle for certain circumstances. So there's 3 of them that we're going to talk about. Here's the first one, the right triangle. So if the diameter of the circle is the hypotenuse of a triangle made by connecting points that are on the circle, then the largest angle is 90 degrees. So I'm talking about this angle up here. And the next inscribed angle theorem that I'm going to talk about is this bow tie pattern. Now I call it the bow tie because it looks kind of like a bow tie. Basically, you have 2 chords connected across. Now, where they meet in the middle, that's not necessarily the center of the circle. I want to make that point clear. This point can be anywhere. But what's important is that these points are on the circle. Okay, so you actually have 2 chords connected like this in a bow tie pattern. Okay, so the rule is corresponding angles are equal. So what are the corresponding angles? Well, we have these two angles. Those are opposite angles, remember from the warm-up. And then these two angles are the same, and these two angles are the same. So if you ever see a bow tie pattern, you'll know that the corresponding angles are equal. The next theorem I want to talk about is, well, I call it the Star Trek symbol. If you're familiar with the TV show Star Trek, you'll recognize this symbol. This is the badge that they wear on their uniforms. Anyway, this is the center of the circle right here. This is a radius. This is a radius. This is a chord. This is a chord. Okay, so if the two radii and these two chords are connected all together to form this Star Trek symbol, the angle at the center is always twice the angle at the outside. So if this angle in here is x, this angle at the center, the subtended angle in here, is twice that, 2x. So if this was 10 degrees in here, this would be 20 degrees out here, etc. Okay, so these are patterns that you should be familiar with if you ever see them in a circle. So for my first example, we're just going to be using the ideas that I had on the previous slide. So I'd like you to pause the video and try this. So we're just finding this angle in here, this angle in here, this angle here, and this angle here. So pause the video, try this on your own using what you had on the previous slide, and then check back in to see how you do. For the first one, here I have the diameter goes through the center of the circle. So that means these two chords are at 90 degrees to each other. Here I have the Star Trek symbol. So I know that this angle inside is half of this angle outside. So it's 80 degrees. Same pattern here. This angle inside is half of this one. So that means theta must be 100 degrees. And here we have the bow tie pattern. So that means these corresponding angles must be equal, so theta is 20 degrees. Now let's talk about the tangent theorem. Okay, so here I have a circle. O represents the origin or the center of the circle. Here's a radius. Here's a radius. This blue line is a tangent, so it meets the circle only at one point. And this is also a tangent. It meets the circle only at one point. Now, the rule is tangent is always perpendicular to radius. So anytime you see a tangent and the radius connected at the same point, you can be sure that that tangent and the radius are perpendicular. They're at right angles, 90 degrees to each other. Now, if we take that same situation where we have tangents connected to the circle and we extend those tangents and both tangents meet at a point, then what I've labeled here, okay, A is the point where those two tangents meet, B is the point where this first tangent meets the circle, C is the point where the other tangent meets the circle, O is the center of the circle. Well, you've got two triangles in here, and we know that triangle AOB is similar to triangle AOC. So AOB, this triangle over here, is similar to triangle AOC, this triangle over here. Okay, so that is true when two tangents meet at a certain point. The triangles that they make with the circle are similar. So what does that mean? Well, similar means that the angles are the same. So this angle in here equals this angle in here. This angle, angle B, is equal to angle C. And this angle up here and this angle in here are both the same. And again, we can use these ideas of the tangent theorem when we solve certain geometry problems with circles. Okay, example 2, find the missing values in each case. So here's my first case. I have a circle. Here's the center. The radius is 3. The radius is connected to a tangent at a point. The tangent is x in length. We don't know how long it is, but we know from the center to this point is 5. So how can we solve for x? Well, if we think about the properties that we have been looking at, if you have a radius and a tangent connected together at a point on the circle, those lines are perpendicular. So this is a right triangle, which means I can use Pythagorean theorem to solve for x. So just be careful when you're doing Pythagorean theorem that you put the hypotenuse in the correct spot. So we have x squared plus 3x equals 5 squared, not 3 squared plus 5 squared equals x squared. Okay, make sure the hypotenuse is by itself. But we can rearrange this, move the plus 3 squared over, so now it's minus 3 squared. 5 squared is 25, minus 3 squared, which is 9, so 25 minus 9 is 16. Take the square root, x is 4 in this case. All right, let's look at the second case. Here I have the center of the circle, a radius meeting a tangent. A radius meeting a tangent. Okay, so when we have the radius and the tangent meeting together at one point, remember that means this angle is 90 degrees, and that's in both cases, here and here. Okay, so now we have two right triangles. Also, let's look at this. Tangent, tangent, meeting at a point. So that means that these triangles are similar to each other, which means all the corresponding angles are equal. And because the two triangles share a common side, we know that the lengths of the sides are also equal. Okay, so x is 9. Okay, so y is equal to 35 degrees. If y is 35 degrees and this is 90 degrees, then z must be whatever adds up to 180 with that, so it ends up being 55 degrees. And then, yes, x and 9 are the same length, so x is 9. Let's look at the third case. Here's a tangent meeting the circle at a point. But this line here, this is not a radius. It does not go through the center of the circle. So this angle x is not 90 degrees here. But what do we know? Well, here's another tangent meeting that same line, and those two tangents are meeting at a point. So because we have two tangents meeting at a point, we know if we were to connect that point to the center of the circle, we would have two similar triangles here, which means that this side and this side are the same. So now that we know this side and this side are the same in this triangle, we have an isosceles triangle, which means this angle and this angle are identical inside this isosceles triangle. So x is 40 degrees. And this last one, well, what's going on here? I got two circles with three tangent lines all meeting at a point. This tangent line segment is 12 units. This one is x, that's the one we're trying to find. Now, on the previous slide, I didn't have a rule that showed tangents with two different circles meeting in a point. So what's going on here? Well, let's just think about it. These two tangents are from the same circle meeting in a point. So that means this one is 12 because these two lines are the same for the same reasoning I had over here. So if this is and this are the same, well, now let's look at the other circle. So on the big circle, I have a tangent here, meeting at a point. Well, this line and this line are the same, so that means x equals 12. So sometimes the questions are more straightforward than others, but you can use any of the tangent theorems that we had on the previous slide to answer these problems. Okay, moving along here, example 3, find the missing values in each case. Well, the missing values is angle x in each case. Now, if you ever see a diagram drawn like this, you'll see, okay, 260 degrees here, but it's outside the circle. What is it referring to? So this notation, if you ever see it, it's referring to this angle right here. So if this angle is 260 degrees, and all the way around a circle is 360 degrees, that means this angle in here must be 100 degrees. Okay, now here's a radius meeting a tangent at a point, so I know this angle is 90 degrees. Here's another radius meeting a tangent at a point, so this angle must be 90 degrees. Now take a look at this. 1, 2, 3, 4 sides to this shape. This is a quadrilateral, which means the total of the interior angles has to equal 360. So if I know 3 of the 4 angles, I can calculate the missing angle by subtracting all the other angles from 360. So I end up with x equals 80 degrees. Now this question is very similar. The 120 degrees is not referring to x. It's not giving you the answer right there. But the 120 degrees actually refers to the subtended angle in here. Now, using the same reasoning as I did over here, well, tangent, radius, they meet at 90 degrees here and here. This is a quadrilateral, so I know the total of the angles has to equal 360. So in this case, x is equal to 60 degrees. Now, if you didn't know that the interior angles of a quadrilateral add up to 360, you could have solved this by cutting this angle in half to join up with this point and using similar triangles, and you could have found half of the angle up here and then multiplied by 2. If you did it that way, you should still end up with the total angle x at the top there is 80 degrees and 60 degrees. Okay? Now, in this example, we're going to determine if the lines are tangent to the circle. Okay, so remember, if you have a radius and a tangent meeting at a point, they should be at 90 degrees to each other. If they meet at 90 degrees to each other, that means you have a right triangle, which also means Pythagorean theorem will work. So really what we're going to do in this question is see if the Pythagorean theorem works. If it works, then we know it's a right triangle, which means this angle must be 90 degrees. So this is how I do a proof with the Pythagorean theorem. So I look at the left side of the equation. That's what LS stands for. The left side of the equation is 6 squared plus 12 squared. The right side is 13.4 squared because 13.4 would be the hypotenuse if this was a right triangle. So 6 squared is 36, 12 squared is 144. Add those together, it's 180. The right side, 13.4 squared, well, it's really close to 180. In fact, I would say that because of imprecision, we could say that because of imprecision in measurements, this is so close that we're just going to say they're the same. Okay, so left side equals right side of the equation. Therefore, the line is tangent. Because as I said, if this line was a tangent to the circle, then it would be at a right angle to this radius, and Pythagorean theorem would work. Left side would equal right side. Okay, let's try this other one. Obviously, this line is not tangent. This one might be, because it looks like it meets the circle at one point. And this line, no, it's not the radius, but it is the diameter. So the diameter and the tangent should be at a right angle with each other. Okay, so let's just do the same thing. 9 squared plus 15 squared should equal 18 squared if this is a right triangle. So I set it up. Left side is 9 squared plus 15 squared equals 306. Right side is 18 squared, which is 324. Those aren't even close. So left side does not equal right side. Therefore, this is not a right triangle. There's not a right angle in here, which means this line is not tangent to the circle. So we've done a lot of examples in this lesson using the different inscribed angle theorems and also the tangent theorem. Use those concepts as you try the practice questions. And if you run into any issues, please let me know and I'll do my best to help.